Hey, welcome to the Explainer. Today, we're cracking the code on something that shows up on pretty much every aptitude test you'll ever take, the number system. This is your key to getting that dream job.
Okay, let's just dive right in with a problem that looks, well, it looks impossible. What is the last digit of 32 to the power of 91? It feels like you need a supercomputer, right? But I promise you, by the end of this, you'll have a super simple trick to solve this in just a few seconds.
See, to crack problems like this, you don't need to be a math whiz. You just need the right mental toolkit. So that's what we're going to do. We're going to build that toolkit together, piece by piece, starting right from the ground up.
All right, so the first tool for our kit is the foundation itself. We've got to understand the different families of numbers. Getting these straight is the absolute first step to seeing the patterns that unlock everything else.
First up, we've got natural numbers. Look, these are just your basic, everyday counting numbers. 1, 2, 3, 100, a million. If you can count it, it's a natural number. Simple as that.
Now, what happens if you take all those natural numbers and just add 0 to the group? Boom! You get whole numbers. It's the same set, just with the very important idea of nothing included.
Integers are where we expand our number line into the negatives. So think of it as all the whole numbers and their mirror images on the other side of 0. -2, 0, +5, they're all integers. And then you have the numbers that live in between the integers. Rational numbers are the friendly ones. Any number you can write as a neat fraction, like 1/2 or 3/4. Irrational numbers, though, are the wild ones. Think of pi, or the square root of 2. Their decimals go on forever without repeating. Put them all together, and you have the complete set of real numbers.
And here's why knowing all that matters. It leads us to our next tool, divisibility rules. These are absolute lifesavers. In a timed exam, every second counts, and instead of doing long division, these rules let you just glance at a number and know its secrets. This is how you start working smarter, not harder.
I mean, just look at how elegant some of these are. Divisible by 2, just check the last digit. By 3 or 9, just add up all the digits. It's amazing. And that rule for 11, it's a fantastic little puzzle that we're about to use. These aren't just random tricks. They're shortcuts based on the deep structure of how numbers actually work.
Okay, let's put that rule for 11 to the test with a classic exam question. We've got a 6-digit number here, but one digit is missing. It's x. We're told the whole number is divisible by 11. So our job is to find the value of x. And no long division allowed.
Here is how that rule works its magic. First, you take the digits in the odd positions, the first, third, and fifth, and you add them up. So that's 4 plus 9 plus 2, which is 15. Got it? Okay. Now do the same for the even positions. 6 plus 4 plus x, which gives us 10 plus x. The rule says the difference between these two sums has to be 0 or a multiple of 11. Well, to make the difference 0, x minus 5 has to be 0, so x must be 5. See? It's pure logic, not tedious calculation.
All right, let's grab the most powerful tool in our kit. This concept, cyclicity, is the secret weapon that's going to make that impossible opening problem feel like a piece of cake. It's all about finding a hidden rhythm in the numbers. See, we don't need to calculate the entire huge number when we're only asked for the last digit. So let's just focus on that one digit. Watch what happens when we take the number 2 and just keep multiplying it by itself. A beautiful pattern is about to show up.
So let's watch that last digit. 2 to the first power ends in 2. 2 squared is 4, so it ends in 4. 2 cubed is 8. 2 to the fourth is 16, so it ends in 6. Our sequence so far is 2, 4, 8, 6. What do you think comes next?
And there it is. 2 to the power of 5 is 32. The last digit is 2 again. We're right back where we started. If we keep going, the last digits will always follow this same repeating pattern. 2, 4, 8, 6. Then 2, 4, 8, 6, over and over. That is cyclicity. For the number 2, it's a cycle of 4. This gives us a dead simple 4-step trick.
First, ignore everything but the last digit of the base number. That's all that matters. Second, you know its cycle length. For 2, it's 4. Third, you divide the big power by that cycle length. And fourth, the remainder you get from that division tells you exactly where you'll land in the cycle.
Okay, with our cyclicity tool sharpened and ready, let's go back to that original monster problem. It's time to put our new tool to work and just dismantle that scary-looking question from the beginning.
Let's do it. 32 to the power of 91. The last digit of the base, 32, is 2. We know its cycle is 2, 4, 8, 6. Now we just divide the power, 91, by the cycle length, 4. 4 goes into 91 22 times, but what we care about is the remainder, which is 3. That remainder is everything. It means we want the third number in our cycle, 1, 2, 3. The answer is 8, and that's it. Problem solved.
You've got the toolkit. You've seen the concepts in action. Now, the best way to make these skills stick is to actually use them. So, let's put your new knowledge to the test with a couple of quick practice problems.
Here's your first challenge. It's another one of these missing digit puzzles. The number 35269n is divisible by 11. So, what is the value of n? Go ahead, apply that odd-even difference rule we just learned.
So, how'd you do? Let's check the logic. The sum of the odd places, 3, 2, and 9, is 14. The sum of the even places is 5 plus 6 plus n, or 11 plus n. For the difference between them to be 0, 14 has to equal 11 plus n. A little bit of simple algebra, and we find that n has to be 3. Nicely done.
Okay, here's a different kind of puzzle. This one is a pure test of your concepts about remainders. Think about what it means for a number to have a remainder of 3 when it's divided by 6. Don't just guess. Think about the structure of that number.
Let's walk through the logic on this one. A number that leaves a remainder of 3 when divided by 6 can be written as 6 times something plus 3. Let's call it 6k plus 3. Now, we square that whole thing. We get 36k squared plus 36k plus 9. Now, since 36 is divisible by 4, we can completely ignore those first two parts. Their remainder is 0. All we care about is the remainder of 9 divided by 4. And 9 divided by 4 leaves a remainder of 1. That's our answer.
And this just goes to show that so often, the toughest-looking problems are just hiding a simple, elegant pattern. Once you learn to see the pattern, you can solve the problem. The real question is, what will you deconstruct next? Thanks for watching.